Well, dear friend, now in this video I will take extrinsic semiconductors. So, which are extrinsic semiconductors? Extrinsic or impure. They are also called as impure semiconductors. Impure semiconductors. The semiconductors which shows conductivity due to added impurity to pure semiconductor are called extrinsic semiconductor. Extrinsic semiconductors. Actually, pure semiconductor when mixed or doped, for this we use also term doped, doping the impurity to pure semiconductor produce extrinsic semiconductors. Doping, the word is doping, dope karna, doping of impurity to pure semiconductor like silicon and germanium. Actually, germanium and silicon are the best semiconductors. The whole universe, the whole world has been revolutionized by these semiconductors. So, extrinsic semiconductor are two types. The extrinsic semiconductors are of two types further. Number one, N type. So we may write small n type as it is. And number two, P type. We will write also P type. Now, how they are obtained? Actually, how the doping is done, I will discuss. And when we obtain N type or P type semiconductor. So first I will take here N type semiconductor. N type semiconductors. N type. When a pure semiconductor who is pure semiconductor, silicon, germanium. So people use different language. That confuses and difficult to remember. I am using simple language here. When a pure semiconductor is doped with pure semiconductor like silicon, like silicon or germanium. is doped with a pentavalent element like phosphorus, P, or arsenic, arsenic, As, we get N-type semiconductor. I will be telling you why they are called N-type also. This is important here. Now dopant concentration, how much mass of phosphorus or silicon should be added depend upon our requirement, but their atom per unit volume remain much less than that of pure semiconductor. Now I will explain you conductivity of semiconductors, N-type semiconductor, on the basis of covalent bonding as well as energy band diagram. So suppose here it is phosphorus atom. These are silicon atoms here. These are silicon. Please, don't take that. I am not able to draw the whole circle so people. These are representing silicon atoms which are bonded with phosphorus, pentavalent atom. Pentavalent atoms are those which have 5 valence electron or 15th group element. People say like this also 15th group element. Though it is simple to learn 15th group, but we must take care it should be pentavalent. Pentavalent elements have 5 electrons in their outermost orbit or outermost shell कहते हैं. There different nomenclature or theory are there about atom. We say orbital, SPDF, etc. in chemistry. That also. But our aim is there that only we will consider here valence electron. Pentavalent element is that which has 5 valence electron in their orbit. Silicon has its tetravalent. So now all 4 atoms of silicon are shared with phosphorus atom to make single covalent bond. Even at very low temperature, what will be happening? All the electrons are with their bond. Now what will happen to the 5th electron of this phosphorus atom or pentavalent? Pentavalent silicon has 5 valence electron. 4 valence electron of pentavalent get combined with neighboring silicon atoms, 1 remaining unshared. What happens to that unshared electron? That will be donated by phosphorus to the crystal. And as soon as it donates the electron, it becomes positively charged, plus E. Partial positive charge is there and electron is negatively charged. Now, this free electron will be there even at 0 Kelvin. So there is drastic change in the conductivity of semiconductor when they are doped with impurities. So conductivity of extrinsic semiconductors is there because the pentavalent atom donate electron to silicon which remains free, but it is weakly bound with phosphorus atom, weakly bound, like unlike charge attract. It is not totally free. It is not totally free. It needs a small amount of energy to get away from this silicon atom, phosphorus atom. So phosphorus here is called donor, and this electron here is called donated electron. Even at 0 Kelvin, this will be there. And overall silicon itself is intrinsic semiconductor. At normal temperature, there may be some electrons due to thermalization because of intrinsic charge carrier density. But the number of intrinsic charge carrier density here will be much less than the charge carrier produced by donor atom. At ordinary temperature, we dope the silicon, we dope silicon with pentavalent element of desired quantity. That desired quantity of phosphorus or pentavalent element create large number of charge carrier, which are here negative charge carrier. There are, I am telling you student, there are intrinsic charge carrier density also, which is in the form of hole and electron, and therefore number of electron here per unit volume become very much greater than NH. I will tell you in one example numerically that in case of this semiconductor, when we dope silicon with pentavalent, number of electron is very much greater than NH, and therefore conductivity of this N-type semiconductor is totally due to electron which are negative charge carrier. Negative. The word is negative charge carrier. We call this as N-type semiconductor. Why? Because electrons which are negatively charged are majority charge carrier. Since electrons are negative charge carrier, negative charge carriers, charge carriers. So, and these are in majority. So, by doping pure semiconductor, we get a semiconductor which is called N-type. N-type semiconductor. Why it is called so? Because electrons are majority charge carrier which are negative charge carrier. So that this N has been derived from this negative. So they are called negative N-type semiconductor. Now we can explain the conductivity even at this actually semiconductor will show conductivity at very low temperature because it has this it will be number, this number will be small. So the conductivity is not equal to that of metals. Now we have learnt energy band diagram. This is conduction band, this is valence band, and here energy gap less than 3 electron volt. At 0 Kelvin or at room temperature, some electrons are present due to thermal, some holes are there due to thermalization. Though at low temperature, valence band completely occupied by electrons, no energy level vacant. कोई energy level यहाँ vacant नहीं, but at room temperature, some electron may jump from valence band to conduction band. The energy of this donated electron will not be matching with conduction band level and valence band. Where it will lie? The energy of donated electron will lie in energy gap just below the lowest energy level of conduction band, and this is called donor energy state. This is also very important concept. Energy of donated electron. ये जो इलेक्ट्रॉन डोनेट किया है किसने? फॉस्फोरस ने. How much energy is possessed by this? That energy possessed by electron will neither be in conduction band nor in valence band. It will be just below the energy level, lowest energy level of conduction band, and this is called donor energy state or donor energy level. When we apply electric field can provide energy to this because it is small, so that this electron go in conduction band and show conductivity. I hope you have got my point. Dotted line indicates the energy level of donated electron. At very low temperature, valence band completely occupied by electron. I have shown here 2 holes and 2 electrons. These are at room temperature. But if our semiconductor is at very low temperature, then there is electron of this energy. When we apply electric field, electron can gain energy which it required to go from this to this, to go to conduction band, and hence N-type semiconductors show conductivity because of electric field alone only. There is no thermal agitation required. I hope you have got my point. N-type semiconductor, it is called so because it has negative charge carrier in majority. And whole in, I will tell the number. It is like that if I ask to add 10 to the power 16 to 10 to the power 6, what you will say? The result will be 10 to the power 16, sorry. So ये negligible है. Though they have here holes, electron charge carrier, and holes are minority charge carrier. Hole यहाँ होंगे because of intrinsic characteristic of silicon. Silicon itself is intrinsic semiconductor, and intrinsic semiconductor number of holes and electrons are equal, but those holes are small in comparison to donor electrons. Donated electron, this phosphorus atom is called donor atom. The ratio like that. कि अगर ये इलेक्ट्रॉन हैं तो ये होल होंगे, तो इनका एडिशन 10 to the power almost 16. Though 10 to the power 6 means 10 lakh, but it 10 to the power 16, very big. So it is called N-type. Now, in next video I will take P-type semiconductor. Please read, watch this video 2 times or 3 times at one time sitting, in one sitting. ये नहीं कि आज पढ़ लिया तो फिर 10 दिन पढ़ेगा, नहीं. अभी 2 बार पढ़िए, 3 बार. तो आपको याद हो जाएगा, बहुत सिंपल मसला है. दिस चैप्टर इज वेरी सिंपल, बट अनफॉर्चुनेटली स्टूडेंट डू नॉट, आई एम ऑब्जर्विंग दैट माय व्यूअर आर डिक्रीजिंग. This is not good for you. Thank you.